This is concept 50, or next unit. This is the overall unit is trigonometry. Our first one, concept 50, will deal with the Pythagorean theorem, special right triangles, and the basic trigonometric ratios. So first thing we're gonna review here is the Pythagorean theorem. You will recall you have a right triangle, so you have a squared plus b squared is equal to c squared. And my first two examples here are very basic. You're just gonna apply it and find the missing side. For those of you that are not familiar with it, c is always going to be the side opposite to the right angle. That's your hypotenuse. So I get 16 plus 64 is equal to x squared, and then you get 80 is equal to x squared. So from here you take the square root, so you get x is equal to square root of 80. Now it does say give your answer in simplest radical form, so I have to simplify the square root of 80. And if you do this multiple ways, you can do your factor tree, or you can just think what is the biggest perfect square that goes into 80, and when you do that, however you go about it, you're going to get 4 square root 5, and then that would be your answer. The next one, you have identify what your hypotenuse is. So in this case, c is given, so I have 22 squared plus x squared is equal to 24 squared. Okay, so 22 squared, you're gonna get 484 plus x squared. 24 squared, you're gonna get 576, and then subtract 484 from both sides. When you do this, you're gonna get that x squared is equal to 92, and then take the square root, you get that x is equal to square root of 92. So then we got to think again. You could do your factor tree, or just think what's the biggest perfect square that goes into 92 and what that product is, and then simplify from there. But when you do, you're going to get that x is equal to 2 square root of 23. So that wraps up this little section. And why are we doing this again? Because this entire unit deals with right triangles, so we have to be able to know how to solve them. And as they get more complex, as we start throwing angles in them, we're gonna start needing our trig ratios. So next idea is the special right triangles. If you did not learn this last year, what these are is there's two particular triangles, the 45-45-90 and the 30-60-90, and these are very handy ones to remember because they make these type of right triangles very easy to solve. So when you have two similar angles, and we know that angles are properties of a triangle sides, or and vice versa. So 45-45 would mean that the two opposite sides are equal. So I can call both of these x. So then both legs are x. And if you were to do the Pythagorean theorem here, x squared plus x squared is equal to c squared, and then you solve for that c, you're going to get that the hypotenuse is equal to x square root of 2. So what are the x's? X's are the actual given values, as you'll see in these examples here. So you could just plug in and then find those values much faster. The 30-60-90 works same way. 30 would be your smallest side, and then if you go about with the same idea, you're going to get that the other leg is x square root of 3, and then the hypotenuse here would be 2 times the smallest side. So the shorter leg is x, the longer leg is x square root of 3, and then finally the hypotenuse is 2x. So we're going to use the ideas of the special right triangles now to solve these next few examples. So number 3, I have a leg, right, a leg of a triangle, 10, and then I have 45-degree angle here, so I know the other one is a 45. So then I have a 45-45-90. It's this first type of right triangle, and then one leg is 10, so then therefore the other one is 10, and the hypotenuse would be 10 square root of 2, and you're done. The next one, have a 45 degree, so I have a 45 degree here, and then identify the hypotenuse. It's given, so it's 16. Okay, so what do I know from this? I know that the hypotenuse is 16, so it would be x square root of 2 is equal to 16. X square root of 2, like that. So then, and I know these two sides would be equal, your x, right? So what I can do is I can solve for this x, and then you get the measure of both legs. Now, if I divide both sides by square root of 2, I'm going to move up here because I'm running out of space. So I get x is equal to 16 over square root of 2. If you put this in your calculator, you're going to get some decimal. But we can avoid dealing with those type of irrational numbers by just thinking. If you recall from our radicals unit, we don't want to express any value with a radical in the denominator, so I would multiply top and bottom here by square root of 2. In the denominator, square root of 2 times square root of 2, you're going to get 2. In the numerator, you're going to get 16 square root of 2. This is not a z, it's a 2. Then you can simplify 16 over 2, and you get 8 square root of 2. So then that's what both legs of this triangle are. So again, these special right triangles, they are derived using the Pythagorean theorem, and what I just did here is, well, I just generalized the two type of triangles, the 45, 45, 90 and the 30, 60, 90, and I was able to just use this generalization to find or solve for measures of sides of right triangles, and I didn't have to worry about using Pythagorean theorem, or in this case I would be limited because I was missing two sides as opposed to given two sides. So it's a handy thing to memorize, especially come those ACT tests or any future tests where they give you right triangles. These can prove to be real good shortcuts. The next one, I have another 45, 45, and my hypotenuse is given, so therefore these two have to be the same. And this one's a lot more straightforward. Look, 14 square root of 2, I know my hypotenuse has to have this form, some value x square root of 2. If you just match it, right, x is 14. So therefore the two legs have to be 14 because it's x square root of 2. So 14 and 14. Number 7, we have, it's this would be a 30, 60, 90 triangle. So I'm going to be using this guy here, and then my hypotenuse is given, so we could just go from there. So my hypotenuse is 2x, so 8 is equal to 2x. And if you solve for x, you get that x is equal to 4. What's x? X would be the shortest leg, the smaller one. So then in this case, just using the picture, my x is 4. And that would make sense because, again, my hypotenuse is 2x. 2 times 4 is 8, what's given. So then the longer leg would be x square root of 3. So 4 square root of 3. Next one, I have another 30, 60, 90 triangle. This time I am given the longer leg, 27. So looking at my special right triangle, it would be this guy here, so x square root of 3. So then x square root of 3 is equal to 27. So then I would solve for x, what would give me my shortest leg. So x is equal to 27 square root of 3. And again, you can put this in your calculator and you'll get some decimal, and we don't want that. We want to stick to our cleaner numbers. So then you would multiply top and bottom here by square root of 3. This would give you 27 square root of 3 over 3. and then you simplify here, you're going to get 9 square root of 3. So then the smallest leg, x, is equal to 9 square root of 3. That is, whoops, that would be y, right? Y is my shorter leg. So 9 square root of 3. And then x, what's x? X is 2 times x, the shorter leg. If 9 square root of 3 is my shorter leg, I multiply this by 2 and I get 18 square root of 3, which is x. So in this one, the notation they gave us might be a little confusing, just that y is a shorter leg, x is your longer leg. Finally, number 8, we have a 30, 60, 90. The shorter leg is given 5 square root of 6. So let's see, I know that the shortest leg is, so I have x is equal to 5 square root of 6, right? And then I know that, actually let's call this a, as to not confuse, because I already have an x and a y. So to find y, the longer leg, this is my smallest leg, I have to multiply, if x is equal to 5 square root of 6, the longer leg is whatever that shorter leg is times square root of 3. So I could just multiply this times square root of 3 to find what that longer leg is. So, and if you recall, right, how to multiply radicals, you get 5 square root of 18, okay, and then 5 square root of 18. You can actually simplify this. You're gonna get 9 square root of 9 times square root of 2. 9 becomes 3, so you get 15 square root of 2. So then the longer leg, in this case it's y, is 15 square root of 2, and x would be 2 times the smaller one, so multiply this by 2 and you get 10 square root of 6. And that wraps up this section here. Moving on to the next one, some new stuff, some semi-review stuff. We have a trigonometric function is a function whose rule is defined by a trigonometric ratio. A trigonometric ratio compares the lengths of two sides of a triangle. The Greek letter, and this would be theta, and let's see, the way it's pronounced, I know we've talked about this in the past, is like theta, theta, is used to represent the measure of an acute angle in a right triangle. So what we have here is we have our ABC triangle. It's a right triangle. Theta is denoted here. It's SOHCAHTOA. So sine is opposite over hypotenuse, and you can also say this is equal to, if we look at our triangle here, well, theta opposite A over hypotenuse C. So this is A over C. Cosine is adjacent over hypotenuse, and then so here's theta adjacent B over hypotenuse C. So you can say this is also B over C. And then finally tangent TOA, right, in SOHCAHTOA, you got opposite A over B adjacent. So opposite over adjacent, that's equal to A over B. You can also write it on top of your paper here, SOHCAHTOA. So helps you remember again, opposite sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent. Whatever helps you remember the three basic trig identities. What we have here next are the reciprocal functions, or the reciprocal identities. Cosecant, okay, read as cosecant, is 1 over sine theta, okay, and again it's the reciprocal. So if sine is opposite over hypotenuse, cosecant would be hypotenuse over opposite. Okay, and then similarly C over A. The secant is 1 over cosine. So again, reciprocal, so hypotenuse over adjacent. And then that would be C over B. And then finally, cotangent is 1 over tangent. So adjacent, whoops, I just realized I misspelled this here. It should be a J. Adjacent, so you have adjacent over opposite, or B over A. And the way I remember this when I was younger, it was, well, tangent and cotangent are easy to remember that they are the reciprocals here, right? Because tangent is in both of them. Right here, the way I remember was that sine, so if, again, this is the way it worked for me. It starts as cosecant, cosine, but opposite. So sine goes to cosecant, and then cosine goes to secant. Again, whatever helps you remember which reciprocal goes with which, but that's the way it worked. That's the way I was able to remember it. Here are some examples. It says find all 6 trig ratios for theta shown in the triangle below. So we got this triangle here. First thing we should do is maybe solve for the last side. So there's my hypotenuse is missing, so I have 16 squared plus 30 squared is equal to, let's call it x squared or c squared. 16 squared is 256, 30 squared is 900, that's equal to x squared. When you add these two guys up, you get 1156, that's equal to x squared. I believe 1156 is a perfect square, and it is. You get x is equal to 34. So then this guy here is 34. So let's go ahead and label the 6 trig ratios here. So sine, again, it's opposite over hypotenuse. Here's theta, right? So I got 16 over 34. Okay, and then I can simplify this. I get 8 over 17. Cosecant is the reciprocal, right? It's the reciprocal of sine. So you get 34 over 16, and then you can simplify this as 17 over 8. Cosine is adjacent, 30 over hypotenuse, so 30 over 34. And then you can simplify this to 15 over 17. The secant is the reciprocal, so 34 over 30, and that's equal to 17 over 15. Tangent is opposite over adjacent, so 16 over 30. And then you can simplify this to 8 over 15. Cotangent is the reciprocal, 30 over 16, and then that simplifies to 15 over 8. So the next one says give the ratio for cosine theta, find the remaining ratios. So give the cosine, is it talking about the previous? I'm not sure what this one is talking about, so we're just gonna skip it for now. Oh, I see it. Here it is. It's given. I didn't notice this. So okay, let's draw out our right triangle. That was funny. So cosine is adjacent over hypotenuse. So like if we pick this to be our theta, so we have adjacent over hypotenuse, so 2 is there and 3 is my hypotenuse, right? So then I can use this piece of given information here to find the rest. So I have 2 squared plus what would be b squared is equal to 3 squared. So I have 4 plus x squared, that's equal to 9. And then I get x squared is equal to 5. And then I get x is equal to square root of 5. So then this guy here is square root of 5. So then sine is opposite square root of 5 over hypotenuse 3. I can simplify that further. Cosine is 2 over 3, and tangent is opposite square root of 5 over adjacent 2. And I can't simplify that further either. Cosecant would be reciprocals, so I have 3 over square root of 5. But something that happens here is, again, we don't want that root in the denominator, so we're going to get 3 square root of 5 over 5, and we can't simplify from there. Secant is 3 over 2, and then cotangent would be 2 over square root of 5, but then we would have to multiply top and bottom by square root of 5, so I get 2 square root of 5 over 5, and then that's it. So now combining it, right, we had the basic trig ratios, which should have been reviewed. We have reciprocal functions, which was perhaps new, and then we already covered Pythagorean theorem and special right triangles, and then we've kind of, you know, seen it all, how it converges here. We jump into the last section, trig ratios of special angles. So as you notice, we have our special right triangles here again, and let's just label our guys here so that it makes referencing a lot faster. So I have x, 2x, and then x square root of 3. So angles of 30, 60, and 45 are used frequently in trigonometry. You can use your knowledge of the side relationships in special right triangles to find the values of trigonometric ratios. So what we're going to be doing here, which you may or may not be familiar with, is finding those basic trig ratios and these common angles. So these are things that you should always carry with you forward, not just in my class, but pre-cal and calculus and so on, because you will see these a lot. Sine of 45, okay, so just, you know, we'll take this one, opposite over hypotenuse. So I get x is equal to x over x square root of 2. Now I can simplify this, right? X over x cancel, so I get let's see, let's look at it this way. You can look at it that way, you can cancel and then go from there. Or I don't want this guy in the denominator, so I can multiply top and bottom by square root of 2. So I get x square root of 2 over 2x. Right, that's what I get if I multiply top and bottom by square root of 2. So then from here the x's cancel, and I get square root of 2 over 2. So the sine of 45 is square root of 2 over 2, and you can check this in your calculator. What you would have to do first though is go to click mode, and then you would have to switch from radian to degrees, and then if you type in sine of 45, you get this guy here, and then if you take the square root of 2 over 2, you get the same value. So let's do cosine of 45 next. So cosine of 45 is adjacent over hypotenuse, so you get x x over x square root of 2, and then you would notice that this has the exact same setup as sine of 45, and then so this is equal to square root of 2 over 2. So sine of 45 and cosine of 45 have the exact same value, square root of 2 over 2. I think this is the easiest one to remember going forward. Whenever you see this trig ratio of this angle, just know it's square root of 2 over 2. For tangent of 45, okay, we have x opposite over adjacent, so x over x, and then we know that that simplifies to 1. So the tangent of 45 degrees is equal to 1. And of course you can verify this in your calculator. Let's go ahead and verify also cosine 45, and yeah, you do get the same thing. And then finally tangent of 45, you're gonna get 1. So it holds. Sine of 30, so we got to look at our bottom triangle here. We're gonna get 30 over whoops, not 30, what am I thinking, x, okay, opposite over hypotenuse, so x over 2x, and then that simplifies to just 1 over 2. So sine of 30 is a half, and then you can check in your calculators that holds. Cosine of 30 is adjacent x over x square root of 3 over hypotenuse 2x, and then you would simplify, your x's cancel, so that's equal to square root of 3 over 2. And again, input in your calculators and verify. Tangent of 30, we have opposite x over adjacent x square root of 3, and then that simplifies to 1 over square root of 3. But if you just look at it as multiplying top and bottom as square root of 3, because we don't want this guy in the denominator, we're gonna get I should have done this a little higher. I get x square root of 3 over 3x, and then that simplifies to square root of 3 over 3. And again, verifying your calculators. And then finally sine of 60, I get this guy. So we're looking at this angle, opposite x square root of 3 over 2x, and that simplifies to square root of 3 over 2. And then cosine 60, adjacent x over hypotenuse 2x, that simplifies to 1/2. And you might have noticed something already with this row compared to this one. And then finally tangent 60 is opposite x square root of 3 over adjacent x, and that simplifies to square root of 3. So sine of 30, a half. Cosine of 60 is a half. Cosine 30 is square root of 3 over 2. Sine of 60 is square root of 3 over 2. So that's not it's not by chance. We'll see this later once we cover the unit circle again. But so one way to remember, and the way I would just remember is like the sine function tends to come first, sine, cosine, tangent. So Katoa as well. So I would remember that sine of the bigger one, sine of 60, was square root of 3 over 2. Therefore the sine of 30 was 1/2. And then I just remember that the cosine was opposite of that. So if sine of 60 was square root of 3 over 2, cosine 60 was the half. And then cosine of 30 was the square root of 3 over 2. So whatever helps you memorize what each of these are, because again, you're going to be seeing these a whole lot, especially as we go later in this unit. Yeah, you can also touch base with me and just let me know if you're having trouble understanding what's what. But otherwise, a lot of this gets explained further as we go through this unit. So that wraps up Concept 50.